Hello and welcome back. In this video, we are going to look at regression, and this is going to be something that is continuation to the previous video that we had on linear regression. If you haven't already watched the previous video, I would suggest you watch that video so that you get more insight into this video. Now, the difference between the ridge regression and the linear regression that we looked at before is the addition of uh, something called as a regularization term to the ridge regression. So this has regularization, and this has the regularization term included into the objective function or the cost function. And how all of that works, we are going to see that now. So imagine that we have a data set, and let's say we have this data set right here, where we have these are the original data points, and they are arranged something like this. Now, if we try to fit a line through this, what we could do is we could fit a line that goes through and weaves through each and every data point, and that would be one possibility. Another possibility would be that the line that we try to draw or try to fit doesn't necessarily capture the essence of how the data is in here. Maybe the line just simply goes something like this. On the other hand, there can be a fit where the line that we are trying to fit, it sort of generalizes the trend in the data that we have. So maybe the line goes something like this. So that's the green line we have. So what is happening in each of these cases is this particular case where we have the line that weaves through each and every data point, that is called as that situation where the fit is that tight through the data set, that is called as overfit, and that is a problem. It is a problem because if we have a new data point, such as, let's say if the new data point is somewhere here, then it is quite possible that uh, the error in the prediction is going to be much larger. That is to say that this particular overfitted model would not generalize well on a new unseen data set. On the other side, if we look at the fit, which is this one, this particular fit is does not capture the trend in the data that we have. It's not flexible, as you can see. So this is again called as underfit. And when we try to fit a model, the idea is that our model needs to have a compromise between these two. So we have to compromise between high variance, which is this case. So this, we would say this has a high variance, and down here we would say that this has high bias. So this has a high bias, and we need to find a compromise between these two to really able to find a model that would work well on a new unseen dataset. And to enable this particular compromise, that's where we use this term, which is called the regularization. And we'll see how that all comes into play. So to get started, let's go back to the equation that we have seen previously for a linear regression. We have seen that if we have uh, if we have a predicted value y, which is y hat of I, that would be equal to beta 0 plus beta 1 x of I, and here we are imagining that we just have one feature. Now with this equation we can we know that these are called as the weights, or weights of that particular equation, and in literature you might see that these are represented by either w or omega, as you see here. But to stay consistent with the notation previous video, we'll continue using the symbols beta here. Now, with this equation, we also saw that to find the error, what we do is we find the difference between the actual value of yi minus the predicted value y hat of I. And this, then what we also do is we calculate the sum of squares, where first of all we would square the differences. So we would square the differences that we have, and then we would sum them, sum all the differences. So we'll sum all the differences in all the differences that we have. And what this represents is I represents a data point. So if we have in the plot that we have above, let's say if the red is the error, then what we are saying is we are trying to find the difference between the actual value, which is in the blue dot, and the predicted value, which would be the red dot shown here, that is on the fitted line. And the idea, the overall objective that we have is to minimize this error in the red that we have shown. And all we are trying to do here is trying to find out the difference between the actual and predicted values uh, to find the magnitude of the error, and then square the values to sort of get that allows us to get rid of the sign, and it will be all positive. In addition to this, what we can also do to calculate the MAC, as we saw that this was the loss function we used in linear regression, is to calculate the mean of this. So to get the mean, we are simply going to divide this particular value by the number of observations. And here in this case, let's say n is the number of observations or data points that we have. And then the rest of the equation stays the same. So we have y0 minus y hat of I. So nothing new so far. This is the same uh, same uh, same equation that we have been seeing previously. Now, if you go to scikit-learn in the docs, so if you go to scikit-learn docs, if I've been following the intermediate series, you'd know what I'm talking about. So this would be a library for machine learning in Python. In the docs, you'd see that for linear regression, the objective function is written as something as follows. It is written as minimize w, then by, and the notation is xw minus y, and then we are taking the squared L2 norm of this. So that this is given for linear regression, right? This is given for linear regression. And for the ridge regression, there is an additional term attached to this particular objective function. So the first part stays the same. So this part stays the same. We have x w minus y and the squared norm of that. Then in here you would have plus alpha into alpha, and then there will be a squared norm of just the w, as you can see. And this part that is something new in here is called as the regularization term, and what that does is it attaches a penalty to the cost function or objective function. So imagine if the weights are higher, so the objective is that the W has to be as small as possible, and that's what the training iterations are trying to do. But if the model is trying to overfit, in that case the W would be much larger, and because W would be larger, uh, the overall uh, magnitude of this term would be larger, and so uh, there will be more sort of uh, uh, in more motivation to reduce the value of W. So that's how this overfitting would be prevented. I hope that gives you some idea as to how this might work. And then the alpha part is uh, is a hyperparameter, can be tuned to kind of regulate what should be the impact of this regularization term. How if we make the alpha large, let's say 1, then it's going to have uh, uh, the penalty would be much higher, as opposed to if we make it 0. If we set alpha to 0, then this term would be same, this term would go away, and what we would have instead is going to be just the regular linear regression. Yeah. So that's what we have, and this is the objective function or cost function that we are going to now look into further. And if you are wondering how this is, so this is sort of related to what we have above to the MSE, because the y hat of I is nothing but um, the it is nothing but the feature x multiplied by the weights W. So that's the same thing, except that these positions are swapped. We have the original value on the left, here the original value is on the right hand side. Now let's go one step further, and what we can do now is uh, use let's look at let's see how we can calculate the gradients for the cost function. I'm going to remove this part, and we'll leave this on there, or is regression, and I'm going to erase that. All right. Now to calculate the cost function, we can calculate the gradients. We can imagine the cost function written as follows. We have J, which is a function of beta 0 and beta 1. And this is going to be equal to the same values that we see here, which is 1 by n sigma I is equal to, and based on the talks, we could use the letter M here instead of N, because M could represent the number of samples and N represents the number of features. But for now, we'll just go ahead with the N representing the number of samples instead of M. So this goes from 1 to N, and inside of this we have yi minus y hat of I square of this. So that's the first term that we already know exists. In addition to this, we have yet another term, which is the regularization term, which is going to be alpha into beta 1. And I'm writing just beta 1 squared, and I'm writing just this because we are assuming that we are working with only one feature right here, and that's why we just have this one pair of beta and x. So this is our cost function or equation that we are now going to differentiate to calculate the gradients. And so now if we try and find the gradients with respect to beta 0, here is what we would have. We would have partial with respect to beta 0, then we have j, and this would be beta 0, and beta 1 is equal to 1 divided by n, and we have the summation sign. I is equal to 1 to n, and inside of this, sorry about that, inside of this we have the partial, so partial with respect to beta 0, y of I minus y hat of I squared plus alpha, and here again we have partial with respect to beta 0, and this would be beta 1 squared. And when we try and solve this, what we get is as follows: 1 divided by n, then this 2 would come down here, so this 2 would be here, and we have that 2 there, and this again, and this term would stay as is. So I is equal to 1 to n, and inside of this we have y I minus y I hat, and then we would have uh, the differentiation of this term right here, uh, which is going to be with respect to beta, and this is y hat of I. I didn't change the y hat of I here. We could have done that, but I'll do that right now, and this would just be 0. So y hat of I, we can write it as beta 0 plus beta 1 x of I. So this becomes 1 by n 2 sigma I is equal to n, and this is going to be y of I minus, and instead of y hat of I, you can write beta 0 minus beta 1 x of I, that is coming from right here, bit x of I, and then when we differentiate this inner term here, what we would get is follows. Uh, we would have partial with respect to beta 0, partial with respect to beta 0, and here we have yi minus partial with respect to beta 0, and here we have the second term, which is going to be beta 0, and after that we have partial with respect to beta 0 for the next term, partial with respect to beta 0, and this is going to be for the next term beta 1 x of I. And here then if we see, this term will become 0, then this term would become 0, and so this term would become 1 1, and we have minus sign there. So essentially what we would get is minus 2 divided by n, and here we have summation I is equal to 1 to n, and inside of this we have our yi, right, the yi minus beta 0, so I minus beta 0 minus beta 1 x of I, and that's what we have right here. Another point to note is that the convention is that we divide this by 2 right here, and the reason for that is dividing this by 2 allows us to cancel this 2 that's up top there, and so our final equation then becomes minus 1 divided by n sigma I. Again, this goes from 1 to n, and then inside of the parenthesis we have yi, which is the actual value, minus beta 0 minus beta 1 x of I. So this is going to be our equation that allows us to calculate the gradients for the objective function that we have j with respect to beta 0. And the next thing we are going to do is calculate the same gradients with respect to beta 1. Now to calculate the gradients with respect to beta 1, here is what we would write. Partial with respect to beta 1, and this is for j, j of beta 0 and beta 1, that is equal to 1 divided by 2n. I've introduced the 2 right in the beginning. Then we have summation I is equal to 1 to n partial of partial with respect to beta 1 of yi minus beta 0 minus beta 1 x of I and square of that plus alpha plus partial of partial with respect to beta 1 of alpha into beta 1 squared. And again here I'm introducing the 1 by 2 just so that we can cancel the 2 that we would get from the derivative. So this would become 1 by n, 1 by 2 into n, and then this 2 would come out. So we would have 2 into then this particular summation term would come. I is equal to 1 to n, and this will be term inside yi minus beta 0 minus beta 1 x of I, and then we would differentiate the term that inside of this. So partial with respect to beta 1 yi minus partial with respect to beta 1, that's going to be beta 0 minus partial with respect to beta 1, and this is going to be beta 1 x of I. And after that we would have 1 by 2 and the alpha that will come out there, and then we have 2 into beta 1. So these 2 would get cancelled out, this 2 would get cancelled out, this term would be 0, then this term again would be 0. So what we get finally is minus, so this would become minus x of I, so I'm putting that minus sign up front, minus 1 divided by n sigma or summation I is equal to 1 to n. This term stays as is, yi minus beta 0 minus beta 1 x of I and into x of I, which is coming from here, and then plus alpha into beta 1, and this is the gradient with respect to beta 1 when we differentiate the cost function or objective function j. So with this, then we now have all the information that we need to manually calculate the gradients. So let me just write down the uh, function for calculating gradients for beta 0 as well. So this is going to be j beta 0 comma beta 1 is equal to minus 1 divided by n, and this is going to be summation I 1 to n y of I, sorry, y of I, right, y of I minus beta 0 minus beta 1 x of I, and there's nothing else after this, so it's just that. So this is the second equation. So we have 1 and then we have this 2. Based on this, now we can try out one example where we can do the actual calculation. So I have one written here in front of me on piece of paper. I'm just going to copy the numbers. X is equal to, we'll imagine that we have just one feature with 3 data points. So we have 1, 2, 3. Then we are also going to imagine the y value, that is the target value. The actual target value is 2.0, 2.5, and 3.5. In addition, we are going to say that the initial values for beta 0 is 0.5. Likewise, the initial value for beta 1 is again 0.5. We are then going to set the value of alpha is equal to 0.1, and I remember in the previous linear regression video we used alpha as a learning parameter, but here we are going to use that alpha in context of regularization term that is right here, and for learning parameter we'll introduce eta, and again we'll set the value to 0.1. So those are the values we have to start out with. Now we'll calculate the first value in the very first iteration that we are working through this now. We will calculate the value, predicted value of y. So the predicted value of y is given by x dot theta, and theta in our case is simply equal to a vector which holds two values. The one is beta 0 and the other one is beta 1. So beta 0, we know that it is 0.5, and then beta 1, we know that that is 0.5 as well. So the dot product that we are going to do is going to be between x, which is 1, 2, and 3, and we are going to introduce another column here to associate with beta 0, that is going to be just constant, which is 1, 1, 1, and this is going to be dotted with the theta, which is 0.5, as we see here. Now if we perform the calculations, it's going to be as follows. We will multiply this one with this 0.5, so 1 multiplied by 0.5, and then we multiply this one with this 0.5, so plus 1 multiplied by 0.5. Likewise, we are going to repeat the same steps for remaining two rows. 1 multiplied by 0.5 plus 2 multiplied by 0.5, and for the last row we have 1 multiplied by 0.5 plus 3 multiplied by 0.5. And if we try to calculate the final value, we get 0.5 plus 1.5, sorry, 0.5 plus 0.5, that will be 1. Then in the second case, we have 2 times 0.5 is 1 plus 0.5, that would be 1.5. And this is 3 times 0.5 would be 1.5 plus 0.5 is going to be 2. So what we have now are our first predicted values of y in the very first iteration. So these are our predicted values. What we can do next is calculate the error. So the error is simply going to be y, which is the actual value, minus y hat, which is going to be the predicted value of y. And the actual value of y that we assumed was 2.0, 2.5 for the second data point, and 3.5 for the third one. If we subtract our predicted values are a bit off. We have 1.0, 1.5, and the last value is 2.0. And if we perform the subtraction, we get 2 minus 1, we get a value of plus 1. 2.5 minus 1.5, again we get a value of plus 1. And finally 3.5 minus 2.0, we get a value of plus 1.5. So all positive values, and we have the error. Once we have the error, we are now in a position to calculate the gradients. And to calculate the gradients, we need to calculate the gradients with respect to beta 0 and beta 1. And in vectorized format, we could write that as follows: x transpose of x, and then we dot that with the error that we calculated above. So we do that, and then once we dot that with the errors, uh, that will give us the gradients. But I think, right, so when we dot that with the errors, that's this part we are going to get, and then we are going to add the regularization term. So this is something that we need to add, which we haven't done. So that's the difference between this and linear regression, is now we have this extra term, which is the regularization term that we would have to add here. And so we can represent this by some different theta, as you'll see, because this would have a value of 0, because 0 for beta 0, and I'll explain that as we go. So if we transpose this, we would have 1 1 1, we have 1 2 3, and we dot that with the error. Error is 1.0, 1.0, 1.5, and here then we have the regularization term part, where alpha, we have set the value of alpha to as 0.1. So what we could do is we could say that the very first term will set this as 0, and the second term we will set this as alpha times beta 1. Okay, and so this alpha times beta 1, I'm going to replace this by the values that we have. And so what we have for alpha is 0.1, and for beta we have 0.5. So I'm just simply going to write that right here. And when we perform this dot product, we get 1 times, so this 1 times 1 plus 1 times 1 plus 1 times 1.5. We get 1 plus 1 plus 1.5. And then the second case, we get 1 plus 2 plus 3 times 1.5 is 4.5, and plus on this side we have 0, and this becomes 0.05. That's coming from the regularization term. And so now when we uh, add these numbers up, we get 1 plus 1 2 plus 1 3, and so we have 3.5, and then 1 plus 2 is 3 plus 4.5, that becomes 7.5, and then we have plus 0, and this is 0.05. There's one thing I just remembered, is that uh, this particular term would also have before it a value of minus 1 by, so this particular value, this is what I was talking about. So this value of minus 1 by n, we need to have that here, so I'm going to put that minus 1 by here. And so what we would have then is 1 divided by, we have 3 data points, so minus 1 by 3. So again we have minus 1 divided by 3 here, again minus 1 divided by 3. And so when we perform this calculation, we keep going through this. Let's bring this up here, and what we now have is the gradient. Gradients is equal to, this is going to be 3.5 divided by 3. So uh, 3.5 divided by 3, that gives us 1 point, this is going to be minus 1.16666. So I'm going to stop at 167, and then the next one is 7.5 divided by 3, that gets us a minus 2.5, minus 2.5, and we are going to add the values from the next vector there. So this is going to be plus 0.5, and so our final gradients that we get is minus 1.67 and minus 2.5, 2.505. So to keep things simple, I'm just going to say 2.51. We'll just round that off. Now with these new gradients, we can update our value of theta, or update the value of the betas that we had. So this is what we can update now. So this value of 0.5, that we can update right here. And so to perform the updates, here is how we are going to do it. We are going to say theta is equal to theta minus alpha, and here this is going to be, we won't use alpha in this case, we are going to use eta. Say eta, and this is going to be multiplied by gradient that we calculated above. So the value that we would get is going to be theta is our original earlier old theta that we have is 0.5 minus, and the second one is also 0.5 minus eta that we have is again 0.1. So we just put 0.1. That's the learning rate, and then here we have our gradient, which is 1.67, and this is minus 2.51. If we perform this addition, let's see what we get. We have 0.5 minus, this is going to be minus minus will become plus, so this will be plus, and it will be 0.167. Then we have 0.5, again this would minus minus would become plus, and we would have 0.251. And if we add 0.5 to all of these, let's see what we get. 0.167 plus 0.5, that gets us 0.667, and likewise if we add 0.5 to this number, we would get 0.5 plus 2 is 7, so 751. So this is the new value of beta 0 and beta. So the top one is beta 0 and the bottom one is beta 1. What we can do now is we can use these new values to calculate our new predictions. And to do that, what we'll do is I'm just going to write right up here. So let's say we have y, which is going to be our new predictions, is equal to x dot theta. Now the y value that we have is we have, of course, the constants 1, 1, 1 as we did before. Then we have the values from our feature, which is 1, 2, 3. We are going to dot that with the new value of theta that we just calculated, which is 0.667. That's the beta 0. Then we have 0.751. That is the beta 1. And if we perform the calculations, let's see what we get. We have 1 times 0.67, so 1 multiplied by 0.667 plus 1 multiplied by 0.751, and the next one is 1 times 0. Again 1 times 0.667 plus this time we have 2 times 0.751, and the last one is 1 times 0.667 plus 3 times 0.751. And when we perform this addition, what we get is uh, 0.667 plus 0.751, that gets us 1.418. That's the first value. The second value we get is 2 times 0.751 plus 0.667, that gets us 2.169, and then the last one is 3 times 0.751 plus 0.667, that gets us 2.92. And these are our new predictions. So this is new predictions. These are the new predictions that we have. So that's our new y that we have just found out. What we can next then do is we are now in the second iteration. So in this iteration, we can now find the error. So the error, so this is our second iteration. This is our second iteration. And here we were in our first iteration, as you saw. So we are now in the second iteration. Error is going to be equal to the original value, which is right here. That's the original value, which is 2.0, 2.5, and 3.5. So that's the original value we have, and we are going to subtract the value that we just calculated, 1.418, 2.169, and 2.92. So those are the values that we just found out, and what we get in terms of error is 2 minus 1.418, that gives us 0.5 2.82. That's the first value. Then the second one is 2.5, 2.5 minus 2.169. That gets us 0.331. And the last one is 3.5 minus 2.92, and that gets us 0.58. So that is the new error that we have, and then we can use this new error to calculate new set of gradients right here, and so on. The process would continue to update the theta and then go back and update the predicted value. So what we can do before we end this video is calculate the values for MAC. So if we use this particular in the first iteration, the errors that we had was 1, 1, and 1.5. That was the error that we had. So to calculate the MSE, we can do that by which would be the same as we had before. So that's sort of the same formula that we used, uh, which is going to be 1 minus 1 by n sigma I is equal to 1 to n, and here we have yi minus y y hat of I. That's what and the square of that's what the MAC is. And to calculate that MAC using that, what we are simply going to do is MAC is equal to minus 1 by 3, and we are going to square each value. So 1 square plus 1 square plus 1.5 square, and what we get then is minus 1 divided by 3, and this would be 1 plus 1 plus 2.25. So that's 2 plus 2.25, so that will be 4.25. Right? So 1.5 into 1.5, that's 2.25, and we add 2 to that, we have 4.25, and now we'll divide that. So right, there's no minus sign needed. Sorry. We can then divide this by 3 to get our MAC. So the MAC that we have here in the first iteration, our MAC was 1.467. So that was the MAC in the first iteration. We can now calculate the MAC in the second iteration. So let's see how we can do that. Let me just clear that part. So in the second iteration, the MAC would be uh, should be lower, I would hope. MAC, again, this is in the second iteration. We have again 1 by 3, that stays the same. The values that we are not going to square are going to be from this particular this relation that we have. That's the error that we have, which is going to be 0.582 squared. Then we have plus 0.331 squared plus 0.58 squared, and let's see what we get. So so we have 0.582, the square of that, then we have plus 0.331 square of that, then we have plus 0.58 square of that, and what we get, and then divide. So that gets us 0.7846 divided by 3, and if you divide that by 3, you get a value of 0.261. So this is the new value for MAC that we have. As you can see, the values have changed. So that's our value from the first iteration, and this is our MAC from the second. So the MAC has reduced a lot, and what that tells us is that our predicted values are getting closer to actual values. So the actual value is 2, as you can see here, and our predicted value is 1.4, which is which is one step closer to what we found in the previous iteration, which was just 1, and so on for the others. So that was it for this video. I hope in this video you got some additional intuition about the math behind how we can add regularization term with linear regression to uh, to uh, sort of to avoid overfitting, and uh, that is the underlying concept in ridge regression. So this ridge regression video, if you liked it, please give it a thumbs up. Please like, share, and subscribe. Uh, uh, your likes and comments do mean a lot to me, and they help me stay motivated to create more interesting content for you all. Thank you, and I hope to see you all in the next video. Bye for now.